Hello everyone. Now we are going to go further in understanding the boundary layer flow. We will understand the transition from laminar to turbulent boundary layer, and most importantly, how exactly the fluid particle behaves during this transition. To understand this, we are going to consider two distinct fluid particles, or you can also say the fluid layers, which are approaching the flat plate under consideration. Notice that once again the length of all these approaching arrows is equal, which means velocity at all those points is equal, which is equal to mainstream velocity u. It doesn't matter whether you call it u, you call it v, as long as you call it in a capital notation. So capital U indicates the mainstream velocity u. So this flow is approaching the leading edge of the plate. Leading edge means it is the beginning of the development of boundary layer, the location of coordinate system where x is equal to 0, that is origin of the coordinate system. Now firstly we will discuss about this mainstream flow or free stream flow. This fluid layer or fluid particle, as we can see, throughout its progression of the flow, it is not undergoing any change in its direction or in its velocity. It is continuously traveling with the mainstream velocity or free stream velocity, capital U. But what happens with the second particle, which is now getting included in the boundary layer? As soon as this fluid particle or fluid layer becomes a part of boundary layer, the first thing that happens is the occurrence of no-slip boundary condition. Because of no-slip boundary condition, the fluid in immediate contact with the plate surface retards, it comes to a halt, its velocity reduces to 0, and because of that this retardation passes on to the neighboring layers, and because of that the velocity of neighboring layers also reduces. Now because of reduction in such velocity, a velocity gradient is created which remains up to the thickness of boundary layer. After boundary layer, the total velocity is nothing but the free stream velocity for every fluid layer. And then as the flow still progresses within the boundary layer, so we can see that this fluid particle is undergoing certain rotation about its axis, and this rotation magnitude continuously increases. The velocity gradient also increases because the thickness of boundary layer is increasing. In the turbulent boundary layer zone, the rotation effect of this fluid particle or this fluid layer further increases. This is what exactly happens with the fluid particle when it is transitioning from laminar boundary layer to the turbulent boundary layer. This is for your understanding. Now we will understand once again to the same question. We come to the same question, why boundary layer understanding or study of the boundary layer is so much necessary. We'll get back to the basics. The flow approaches from the left side to the plate. The boundary layer develops. There is a velocity gradient. There is no slip boundary condition. The velocity is 0 at this point and slowly it is increasing. Then this is the mainstream flow. But then what happens to the streamlines of the flow? Because of presence of boundary layer, the streamlines of the flow need to deviate themselves away from the boundary layer. And if they are going away from the boundary layer, which means they are going away from the surface itself. And because of this deviation, it directly affects the mass flow rate of the fluid through that particular channel. Let us understand this with the help of a channel or with the help of a pipe. Previously we considered only one plate. Now we are going to consider either two plates or simply a pipe, the cross section of a pipe, and the flow is taking place through the pipe. Now again same conditions. The flow is approaching from the left and it is exiting at the right. As soon as the flow is approaching, the total area available for the flow is the complete pipe area, and velocity of the flow of approach is same at every point, and that's why length of the arrow is same at every point. But then boundary layer development has started and its thickness has progressively increased. This shaded region indicates the boundary layer, while this white region indicates the core area of the pipe which is available for the flow to occur. Now, what is the problem with this? As soon as the boundary layer has started developing, it has given rise to this velocity gradient profile. Velocity is different at different points. Only in certain points in the middle of the pipe, the velocity is as good as free stream velocity, while in the boundary layer it is lesser. Also, as the thickness of boundary layer is increasing, area available for the flow is reducing. Then what is the problem with this situation? The problem is with the expression of continuity equation. This is well-known continuity equation, which is a beautiful expression that tells us about dependence of mass flow rate on density, area of the flow, and velocity of the flow. The density of the fluid is a very important characteristic because that directly tells you about whether the flow is compressible or incompressible. Now, if the mass flow rate through this pipe has to be constant, which is indicated by the expression C over here, then this total product rho AV has to be constant at the inlet as well as at the outlet of the pipe. Now, what does this constant mean? This constant means that when we apply this continuity equation to two particular sections, to two different sections in a pipe, still the product will be a constant, which means the product rho AV, at the inlet at point 1 should be equal to the product rho AV at the exit or at the outlet. Again, remember, individual quantities of the flow might change, but the total product has to remain constant if continuity equation has to be satisfied. It means that when we express it further, density at point 1, area at point 1, and velocity at point 1 should be equal to, this entire product should be equal to the product of density at point 2, area at point 2, and velocity at point 2. Now, what's the problem? Let us assume that the fluid is the simplest one, water. Why water? Because water is an incompressible fluid, which means density at point 1 will be equal to density at point 2. So these two quantities will nullify each other, they will absorb each other. So the only concern is about the product of area into velocity at point 1 and product of area and velocity at point 2. This product, as we already know, is called as flow rate, which is expressed in meter cube per second. Unit of area is meter square and unit of velocity is meter per second. So the unit of this total flow rate is meter cube per second. Now, at the entrance, area is more. Again, remember from this diagram, at the entrance, area is more. That's why in order to maintain a constant flow rate, the velocity should be less. But then at the exit, area has reduced. And if I still want the same flow rate of water, I need to increase the velocity so that this total product remains constant and equal to the product at the entrance. For an example, if total flow rate required, that is product of area and velocity required, is 100 meter cube per second. Remember that density we have assumed constant. So if the total flow rate required is 100 meter cube per second, area available at the inlet is 20 meter square, then the velocity required will be only 5 meter per second. On the other hand, at the exit, if area reduces to 10 meter square, then in order to keep the total flow rate 100 meter cube per second constant, we need to increase the velocity, which means now velocity has to become 10 meter per second as well. So that's why previously the thickness of this arrow was this much, but as the area is reducing, the length of this arrow is progressively increasing, because in any condition we have to maintain the constant flow rate of that fluid through the pipe. This is again visible in this third diagram. Approach velocity has some arrow length, and as the boundary layer thickness increases, what happens with this is that the velocity profile also has to change. This is the predicted velocity profile or predicted velocity gradient profile, while this is the apparent or which should be available if we want to continue with the flow, which means velocity at every point should be increased if we want to maintain that constant flow rate. So now in every diagram, what we see is that because of the presence of boundary layer, the streamlines of the main flow are deflecting from their original path. They need to deflect, they need to accelerate, they need to increase their velocity if you want to maintain the mass flow rate constant. Now, what is the problem with acceleration of the flow? What is the problem with increase in velocity? This becomes particularly important, let us say, when you are pumping oil through the pipe. Oils have very high viscosity. So because of that, once the boundary layer has formed, because of that formation of boundary layer, the velocity of the oil has to be increased through the pipe. And as we also know the Darcy-Weisbach equation, and in that equation velocity is in numerator, which means as you increase the velocity, the head loss due to friction also increases, which means the pump has to be supplied with extra power if you want to maintain the same mass flow rate through the pipe. All these happens only because of formation of boundary layer. That's it for now. If you like the video, please subscribe to the channel and press the bell icon. Thank you.